In this video capsule, we shall begin our discussion on the magnetics. We need to design the forward converter transformer, and then following that we need to design the magnetics for the inductor. So these two important topics we will discuss. We will see how we go about choosing the core for the transformer, and then later on for the inductor, and also to decide on the number of turns, the thickness of the copper wire that you would use, and all those things for both the forward converter transformer and the inductor. For this, we will use an approach called the area product approach, and follow through in a systematic step-by-step manner. The magnetics is a topic which is generally difficult to understand because we are not able to see within the magnetics. But there are few simple rules, and if we follow them, we generally will not go wrong. And transformers, as you see here, this is a low frequency transformer used in 50 hertz applications, but this is not what we would use in switched mode power semiconductor applications where we would use a high frequency core like the ferrite cores. And therefore, designing the physical magnetics and trying to relate it to the electrical parameters of the voltages and the current that we have been looking at till now is the main core issue in the design of this transformer and the inductor, and that is what we will be doing in this video capsule. I have here a transformer with me. This is a low frequency transformer, and you see here that it is composed of stacked laminations. These are thin laminations stacked together, and then varnish is applied to keep the air pockets out. And these laminations are made of steel. In fact, they are made of silicon steel, and they are called cold rolled silicon steel, and they have maximum flux density capability of around 1.2 Tesla. So these are the common transformers which you would have seen, but these are for low frequency applications or 50 hertz applications. And if I rotate it over, you could probably see that this is where the winding is housed, and this is a parchment paper, and underneath is the copper winding. Both the primary and the secondary are wound here, and then they come out and then terminated here. So this is a low frequency transformer, just to give you an idea how a normal 50 hertz transformer looks like. But for switched mode power supply applications, we will not be using this material. We will be using a high frequency material, something like what is called as the ferrite core. I have here one more example of ferrite cores. You see that this is a ferrite core. What you see here is a ferrite core. This is a round topology ferrite core. It's called a pot core, in fact. This is an SMPS made by the students in the lab. And you see here, there is a former, and within the former, there is the copper coils wound. In fact, you can get a much more clearer picture on a broken ferrite core here. You see that the ferrite core is broken, and within that is the former. This is a circular bobbin, and within the bobbin you have the windings, primary and the secondary windings. So something like this type of core material we will be using. And what is very common in the switched mode power converter or DC-DC converter world is the EE type of core. So this is an EE type of core. So this EE type of core comes in as pair. You will see that two E's are joined together like that, and this forms the E core. And you should understand that the area which is inside, the area of this rectangle which I am pointing out, is the window area. Area 1 rectangle, not both, is the window area AW, which I just mentioned before. And all the windings will have to fit in this window area. And if I remove this two parts, and then if I show to you the facing part, this portion, what you see is the core cross section area. When you put the winding here and the flux flows in orthogonally to this core cross section, this is the core cross section area, and this then splits into two half core cross sections. So actually this is a bobbin, and on the bobbin the windings are wound. So then after winding, the bobbins are inserted into the core to form a completed transformer. So you will see that here this portion is the window area which I was saying, and the windings fill up here. So if I make a cut section, you will just see circles of the copper here in the window area. And apparently the thickness of the wires will be determined by the amount of power and the current that it has to handle. So understand, when I mean window area, it is this area, and when I mean core cross-section area, it is the core cross-section area of the core itself, what you would be using. So with this visual background, let us go back to our notepad and start writing the equations for design.
We shall first take up the design of the transformer to start with, and then later on take up the inductor design. So in the transformer design, on the electrical side, I should say from the electrical perspective, we have the following data with us. We have the voltage of the primary, voltage of the secondary, because of the turns ratio, current flowing through the primary, current flowing through the secondary, and the power handling capability of the transformer. So on the electrical side, these are the aspects that we have with us. Now on the physical or the mechanical side, we have a core, and if you look at the core data sheets, there are two important parameters that will be given. One is called as the core cross section area. Let us see what that means. This is the core cross section area, and there is another important parameter given in the data sheets called AW, also called the window area. So on the physical side, we have the core cross section area and the window area. On the electrical side, we have the voltages and the currents known to us. How do we connect these two and come up with a choice or a selection of a core? Now that is the exercise. So before we go further in the design, I would like to show some cores so that you get an idea of what this core cross section area is, what is this window area. It will help you in identifying these two areas in any given core, and also help you in selection of the cores. So let us begin by relating voltage and AC, the core cross section area. The voltage and AC can be related, so the core cross section area will give you an idea on the voltage withstanding capability of the windings, and the current carrying capability is determined by the thickness of the gauge of the copper that you use for the winding, and they have to be accommodated within the window area. So the current and the window area will get related. So these two relations we shall establish, and in doing that we will actually be arriving at the design for the transformer, and similarly for the inductor. We know from Faraday's law, V is equal to L di by dt, and which is equal to N d phi by dt. So you see that the electrical parameter gets related to the parameter within the magnetic material, which is the flux. So taking those two, we see that voltage is related by N AC dB by dt, where B is the flux density. Flux density B is actually the flux by the core cross section area. So these are a fundamental relationship. I will be reviewing them as we go along, just in case you have forgotten, you can probably start recalling them. Now this is an important relationship we will use. Now consider the forward transformer. So in the case of the forward transformer, I will say this is the primary, which is connected to V in, and then you have the secondary, and you also have the third winding with the demagnetized winding. We'll come to that later, because that contains almost negligible power. So let us say this winding is having NP number of turns and this is having NS number of turns, and across this winding, when the transistor is on, you will see a voltage of V in. Now we will apply that V in, which is equal to NP into AC core cross section area dB by dt, and which is equal to NP into AC, and because the flux transitions are linear in nature, I will, without loss of generality, I could say it is delta V by delta T. Now if you look at the forward converter, we saw the flux phi waveform take similar wave shape like the current. So we saw that flux went from 0 to phi m, and flux either went in a linear way or in an exponential decay way, depending upon whether it was a lossy or lossless, again back to 0. And then after some time, it again, next cycle, started going in this fashion. So there is a swing of 0 to phi m, and if you take in terms of B, there is a swing of 0 to Bm. Bm is nothing but phi m by AC, and we have already put AC there. So this is NP into AC. It can swing a maximum of Bm, and in what time? The time period is this is dTs. And in the case of the forward converter, we know that the on time cannot go beyond 50% of the duty cycle, 50% of the total period. So D is 0.5 max. Therefore, let us say worst case, this can be Ts by 2. So V in is equal to 2 times NP AC Bm Fs. Sorry, correct this to AC. Now this is a very important relationship. This is one relationship which relates the voltage to many other physical parameters. See, the voltage is related to number of turns, core cross section area, the magnetic materials Bm. So in the case of ferrites, Bm will be around 0.2 Tesla. You see the saturating flux density for the ferrites is 0.3 Tesla. So allow around 0.2 Tesla. And the frequency is your switching frequency. It could be 10 kilohertz, 20 kilohertz, depending upon what you are setting as the switching frequency. So this is one part of our work done. We now have to relate the current to the window area, which we will do now. Now the windings will have to fit within the window area. So I will take the example of the EE core. So the EE core can be drawn, the cross section of the EE core. I'm going to draw that, and this is in this fashion. I think we saw this just now physically, but I am going to draw this so that it becomes easier to explain. Yes, and then you have the two EE parts. Yeah, now it's complete. You see the two E sections joined together to form the core, and these two rectangles that you are seeing are the window area rectangles. So this area here is called the window area. However, you should know, you saw that there was a bobbin. There is a part of the window area which goes off for bobbin. So let us say there is a part of it which goes off for bobbin, and then the windings are placed in this fashion. When you are winding them, it comes on both sides, and both sides you will see the bobbin coming into the picture. The windings encircle the bobbin in this fashion. You will notice that when you are placing two conductors, there will be gaps here. These are not filled. So this is also loss of some of the area. And if you are having multiple windings, primary, secondary 1, secondary 2, so on, every layer is separated by insulation layer. Then you will have another secondary, and if you are having multiple secondaries, you will have one more layer of insulation, and this also will eat up into the available window area. So what you should understand is the whole window area is not available to you. There is a factor kW. Now kW is less than 1, and kWAW is the available window area. So it is lesser than, much lesser than AW. So kW is called the window factor. And this window factor can vary from transformer application to application, but in general it goes most on experience. So kW, you can take it as 0.4 for transformers. Two winding or three winding transformers, and is equal to 0.6 for inductors. Inductors have just normally single winding, and there are no insulation between windings and things like that. and therefore you can utilize the window area much better. Also remember that if there are multiple windings, the kW window factor can go as low as 0.2 for multiple secondaries. So these are some things that you need to take into account. So kWAW should fit what? Should be greater than. It should fit NP number of turns with wire cross section area of the primary wire plus NS number of turns with wire cross section of the secondary wire plus ND number of turns of the demagnetizing winding, the wire cross section of the demagnetizing wire. So when I say wire cross section area, when I am having a conductor, copper conductor, so this is the wire cross section area, AW. So it could be AWP for primary wire cross section area, AWS for the secondary wire cross section area, or AWD. Normally the wires come also with an enamel around that, so that it insulates when you are winding. The touching windings should not become a short circuit, so it is enameled and insulated in that way. That also is another cause for loss of window area. So this relationship is important. Now let us say, for example, we know the RMS value of current that should flow through each of the windings. So RMS value of current flowing through the primary, we know that. From the electrical perspective, RMS value of the current flowing through the secondary is known. RMS value of the current flowing through the demagnetizing winding. So if you know that, then there is another new term that I am going to introduce called J. You may or may not have used it. J is called the current density. For different materials like copper, aluminum, there is a particular current density that is allowed as a standard. It's an international standard. So this is generally in terms of amps per square. So generally, for a default, for starting value, you can take 3 amp per square. You can allow 3 amps per square. For every square of cross section area, if you can allow 3 amps for every 1 square of cross section area of the conductor. So this will work out to be 3 into 10 to the power of 6 amps per meter square in SI units. So this is the current density. So current density is something, once copper, you have decided you are going to use copper conductors, you start with 3 amp per square. People in the industry, depending upon the quality of the manufacturer, they go even up to 6 amp per square. So the current density, I RMS value divided by J, will give you the area of cross section of the wire. So you will go and look into the data sheet and check for the wire gauge size. It is called standard wire gauge size in the wire data sheet or wire table, or you can also go on to the internet and use the standard wire gauge table. You know the value of the RMS, you know what should be the current density, which is an amp per square or amp per meter square. You will calculate some wire cross section area requirement. You go into the wire table, standard wire gauge table, and pick that wire gauge which has a cross section area greater than this calculated, and set that one as AWP or AWS or AWD, depending upon the which winding that you are going to use for. So now what we shall do is I'll put it as in this form. I will take the peak value. In the case of the forward converter, we have the currents flowing in this fashion. We have the currents flowing in this fashion. Okay, so I am going to equate it. I'm going to take the equivalent current as square pulsed current. So within this on time, I will say this area is same as this area, and this can be taken as, let us say, Im. So IRMS value can be taken as the peak value into root of the duty cycle, or you could say IRMS into IRMS is equal to Im into form factor, and form factor in the case of square waveform is 1. So A wire cross section area will be KF. Sorry, I should have written it in the other way. Im equals IRMS into Kf, the form factor. So Im by Kfj will be the wire cross section. So if it is for primary, this will be Im for the primary. If it is for the secondary, it will be Im for the secondary by Kfj, and so on. And all this Np, number of turns, into Imp by Kfj plus Ns, number of turns, Ims by Kfj, should all be less than Kw Aw. Now that is another relationship which relates Aw with the current parameter, Kfj is the current density, and the number of turns. Now these two relationships, one with Aw and the other with AC, core cross section area, are the core relationships that we will use. So if I take the product, one is AC into Aw. Now AC into Aw will give you a product called area product AP. This is in meter to the power of 4. This product is this area product is a parameter that you can use for choosing the core. So if you look at the core data sheet, there is a parameter called area product. Sometime it is given, or AC and Aw will be giving you multiply and then find out the area product. So you can list down the area products and you can choose that area product which is higher than the calculated area product. So you can derive with those two equations for each of the transformer topologies, and for the forward converter, it is given in this form. P naught is the output power, 1 plus 1 by efficiency. Efficiency is assumed at around 80%, divided by root 2 into Kw into J, into Fs, into Bm. So this is the area product for the forward converter. And you see that P naught is available from spec. This is a spec input to the design. Efficiency, you can assume it to be around 0.8, 80%. KW, you have a starting figure which I told you start with around 0.4. J, you start with 3 amp per mm square, or 3 into 10 to the power of 6 amp per meter square. Fs is the switching frequency, and this is a design spec again. And Bm for ferrite, you can design your transformer core at 0.2 Tesla. Remember that for most of the ferrites, the saturation flux density is 0.3 Tesla, and you can safely design at 0.2 Tesla. But there are cores, high frequency cores like powdered iron, amorphous cores with brand name Metclass. They have pretty high saturation flux density around 1.6, so you can safely design at around 1.5 Tesla, which will give you a much smaller size core. So in this way you can find out the area product. Once you plug in this value for a particular application, find out the area product, go into the data sheet, pick up that core which has an area product greater than what is calculated. That will give you the size of the core. So let us now list down step by step the design process for the transformer. Let us summarize and list the design steps for the transformer. So first we start with P naught calculation, P naught estimation. So we know V naught, we know I naught, these are coming from spec, and you can evaluate the P naught value. Next, once you know P naught value, you can evaluate the area product AP, and for this you need to assume a switching frequency, and switching frequency is a designer choice depending upon what devices that you are going to use, how fast the MOSFETs are going to be. You may want to switch at 20 kHz, 50 kHz or 100 kHz. And then you use Bm, and if it's ferrite, you can start with a value of 0.2 Tesla. Then afterwards you choose the turns for NP. Now this is coming from, now you saw that V in is equal to 2 NP AC Bm Fs. This is known, this is known, this is known, this is known, because you have already calculated. You have chosen the core. The moment you choose the core, AC is known and Bm is known, Fs is known, Vin is known, only NP is not known. Calculate this. Then afterwards calculate Ns using Ns by Np is equal to N, and N is a spec again, design spec, because we would like to use it in N Vin into D, which is equal to V naught. So V naught is a spec, Vin is a spec, D and N will come into the picture there. So N can be a design spec, designer spec. Then after that, choose the wire gauges, sizes of the copper. So knowing the RMS value, evaluate what should be the wire cross section for the primary, wire cross section for the secondary, wire cross section for the demagnetizing windings, knowing the currents that are flowing through the windings, and choose the wire gauge from the standard wire gauge table, And for the wire that you have chosen, note down the cross section area and then use that to do a cross check. NP into wire cross section area of the primary plus NS into wire cross section area of the secondary plus ND into wire cross section area of the demagnetizing winding. All this put together should be accommodated within the window area, not only the window area, within the available window area. So all this should be less than kW AW. So make this cross check. AW value is known moment you choose the core from the area product value. Moment you do all these things, the design of the transformer is complete. You just have to buy the various materials, the core, the number of turns, the gauge with that particular gauge, bobbin, wind them together and then stack them and put them together. This way you can physically design the transformer from the electrical spec, starting from the electrical spec.